As Dirk says, I'm interested in collective behavior and in particular, how individuals use the information that they get from seeing what others do in order to make their own decisions. And I hope we can all agree that the choices others make are an important source of social information for individuals who find themselves in groups. A canonical example of such is if you're trying to find a good restaurant, especially in an unfamiliar place. We might imagine that if we see one restaurant in which there are lots of people are clearly having a good time, that this is a very positive signal that people have chosen this restaurant over potential other alternatives because they know something we don't about the quality of the possible options. And conversely, if we see a suspiciously empty restaurant like we have on the right-hand side here, this is a very poor social signal because clearly the restaurant is there and available and others have shunned it in favor of what they consider to be better options somewhere else. So when we lack information about an option, or even when we have some information but it's noisy, we can use what others choose in order to improve the decisions that we ourselves make. I have some first-hand knowledge of actually using this, incidentally, in Zurich, which I first visited a number of years before I joined Dirk's group. And we wandered down to the old town and we simply chose the most popular looking beer hall in the old town. And it was the famous Rheinfelder beer Halle, which serves the jumbo cordon bleu, which anyone who was also in Dirk's group 10 years ago will remember me pestering them endlessly to go and visit again. But anyone who's ever been to a very touristy city can know that this sort of strategy is quite fraught with danger as well, because often if we go to the most touristy part of a city, we see restaurants that are very full, and we've probably all had the experience of going into one and then finding that the food isn't actually that good. And on reflection, what often happens is that people merely follow each other into a randomly chosen restaurant, and you get this information cascade where people don't consider how much others are likely to know. So if we're going to be rational about how we use social information, we have to consider what is it that we expect others do know, what information might they have, who else might they have paid attention to, and so on, to make best use of the social information that we can. So I tried to get sort of to the heart of this question about how rational agents should use social information by considering a very simple scenario of agents sequentially choosing between two abstract options, which we can label as A and B, and we might think of these as two doors behind which I have stashed a reward behind one. And so the agents are seeking to choose the door where there is a reward behind it, but they are obviously unaware until they choose which side the reward might be on. And so we can imagine these agents sequentially entering the square box on this slide, and they get a little bit of private information, a private signal about the relative qualities of options A and B. But then they also see what everyone in front of them has done as well. And their goal is to choose the side that has the reward. So we'll define a variable x, which is 1 if A is correct, and x is -1 if B is correct. And each agent is trying to make inferences about the likely value of x. So as I said, each agent has some sort of private information about this. So an agent can make a decision all by itself, but to make the situation interesting, we have to assume that these signals are noisy, so that the agent is uncertain on the basis of its own information alone which choice is the better one. So we'll imagine that agents get a signal, which I've labeled here as delta, which is normally distributed around the true value of x, with some noise epsilon. And epsilon is a parameter which we can vary to make private signals more or less reliable. So if epsilon is very small, then agents can trust their own information very strongly. And conversely, if epsilon is very large, they have very little private information to go on. And for the sake of the model we're discussing right now, we'll assume that epsilon is the same for all agents, so there are no special experts, and the agent's bits of private information are independent, conditioned on the true value of x. Then agents can potentially utilize a second source of information, which are the choices that they see others making. So these are choices which are observed by everyone. So everyone can see the full sequence of decisions that are put in front of them. These are public information, and they're common knowledge in the sense that they can see everything, and they know that all other agents can see them as well. So I'm going to just give a sketch of the sort of mathematical structure of this model. I'm going to skip over a lot of the details because they're not really essential for understanding how the model works, but I will give a link at the end of the talk to a paper that has more of the mathematical details as well. And please do ask me any questions after the talk if you'd like some more details. But just to sketch it out, what happens is that the first agent gets a piece of private information, and because they have nothing else to go on, they are sort of forced rationally to follow the direction of that private information. So if delta 1, for example, is greater than 0, then as far as agent 1 is concerned, that makes it more probable that the reward is behind A, and vice versa. If it's less than 0, they should choose B. So their decision is quite straightforward. It gets more interesting when we consider what the second agent does. So let's imagine, for the sake of argument, that the first agent has chosen A. The second agent, if their private signal also favors A, then there's no conflict and they might as well choose A as well. But if their private signal favors B, so if it's less than 0, they would have chosen B if left to their own devices, but now they've got this extra source of information from the decision agent 1 made. And so their job as a rational agent is to try and balance those two competing sources of information and see which is stronger. And they do this by essentially integrating over or averaging over all of the possible values that delta 1 could have taken. So they're not communicating directly with agent 1 and sharing information, but they can see from the choice that agent 1 makes that delta 1 was greater than 0. And so they can sort of work out, well, what did I expect it would be if it was greater than 0? And how does that weigh against my own piece of information, delta 2? And there is some sort of threshold where if their own signal is greater than that threshold, they will subsequently eventually choose option A. And if it's less than that threshold, they should rationally choose option B. And we can follow this procedure recursively for every agent in the group. So when agent 3 eventually comes to make their decision, they've got a piece of private information as well. When they're trying to weigh that against what they've seen in front of them, they have to consider what agent 1 did, but also what agent 2 did. And when they're considering what agent 2 did, they have to be thinking, well, agent 2 could see agent 1, so they have to consider how agent 2 thinks about agent 1. And what this effectively does means that each agent can place bounds on the information that they know everyone else in front of them has. So they can place a bound on the information of agent 1. They can say whether their information was greater or less than 0. For agent 2, they can tell whether their signal was greater or less than some additional threshold, and so on, all the way back to the last agent in the group. So each new agent that makes a decision is generally likely to provide slightly less information because the bounds become different over time, such that the decisions in front of you become more and more predictable and therefore less surprising and less informative. So we can then ask, well, if we get agents and they follow these rational rules, which we can calculate, what should that sort of look like to us in the real world, and what consequences does it have? Now, I'm mostly a sort of biologist by habit and by sort of the community of researchers that I move in. So I tend to look at these models in a very similar way to the way that biologists actually study real biological systems and try and characterize the social responses. So one way we can do that is to ask, if we actually had these individuals in the lab and we monitored them, how often would we see them choose option A, conditioned on the number of individuals who've already chosen A or B before them? So if we imagine a scenario in which we've really placed, say, the reward behind option A, so there are real signals coming from A, we would get something that looks like the plot on the left-hand side here. So you can see here that there's an overall bias towards choosing option A. So this shows the probability that I will choose A, conditioned on a given number of agents on A and B already. So the numbers are generally biased towards choosing A, but there's obviously a very strong social response as well. So if you have a strong majority already who've gone to B, then you are more likely to choose B as well. And we can play that out to see how it operates on the collective level as well. So we can ask, once this experiment is finished, if we have, say, 15 agents, how many will have chosen A and B? And if we do that, we see that there's, in about 50% of occasions, we get everyone choosing option A, and then an additional sort of 15% where 14 out of 15 do. So there's a very strong bias towards choosing A as a sort of consensus group choice. There's very little probability that they will sort of split half and half, so almost no chance that you get sort of 7 or 8 individuals choosing A. But then there's this considerable probability over on the left, reaching nearly to 10%, of times when everyone chooses B. So you get this sort of maladaptive information cascade, so everyone ends up choosing the wrong option as they follow each other. So these are ways that we can characterize the social response and try to imagine learning about it empirically if we didn't know the actual sort of cognitive process the agents were going through. But so far, what we've considered is a situation where agents try to make the best choice for the choice that happens to be in front of them right now. So they simply try to optimize the probability that they will get the reward behind one of these doors. And that is indeed how the majority of people who've approached this question have previously done it. So there are a number of studies, some of which are my own, some of which are by other people, stretching back a couple of decades now. And they generally ask this same question: what should agents do in order to maximize the chance of getting either the reward or the most reward out of this one choice? What sort of social decision rules does that lead to? But in fact, decisions should often not be seen in that isolation. So often the decisions that we make have longer term impacts on our life history than simply getting a reward now. So we could sort of caricature this by imagining we have a bunch of people here who are choosing one of 2 restaurants to go to, and they're deciding amongst themselves in the normal way, but there's a complication, which is when they eventually choose between the 2 restaurants, they subsequently are likely to make further choices. So they're going to probably make decisions such as, shall we go on and see a film? Shall we go to the pub? If we go to those, which film should we see? What drinks, to which table should we sit at, etc. So you have a whole sequence of decisions that lie in the future of these agents. And they are placed in a context where the group that they make a decision with now, those who they agree with, will form the social group for them to make a decision in the future. So here they've split into 2 groups, and those who've gone to restaurant A are now faced with making future decisions in a smaller group than those who've gone to restaurant B. So even if they thought that restaurant A was the better restaurant, they've lost something, because we know that bigger groups generally should make better decisions because they will have, in aggregate, more information. And so those individuals are going to lose out potentially by not having access to as much collective wisdom when they have to make future decisions. So mathematically, we can characterize this via a recursion where we define the total reward that the agents can expect as the reward that they are expected to get on the decision right in front of them, R1, but then a subsequently discounted reward for all future decisions. And this can be quantified via a discount factor gamma, where gamma either sort of represents how much less we care about rewards in the future, or alternatively, we imagine that the sequence of decisions may end at some point, and gamma represents the probability that each game is sort of the last in the sequence. And so the agent's new goal, rather than trying to optimize the rewards directly in front of them, is to optimize their total reward over these iterated decisions. And the expectations of the rewards in, say, the first, second, third, fourth, etc. rounds will all change depending on the size of the groups that they expect to end up in as a function of the earlier decisions that they make. So we can recharacterize empirically what those decision rules start to look like if the agents continue to perform rationally, but with this changed objective, where they try to maximize rewards over longer timescales. So on the left-hand side, in plots A and D, you see the plots I showed earlier. So this is for an agent with gamma equals 0, where they care not at all about anything beyond the decision in front of them. But if we say take gamma equals 0.9, which corresponds to, say, an expected 10 games in front of us, then their apparent sociality becomes a great deal stronger. What you can see is that these contour lines collapse in towards the center, indicating that agents become much more likely to follow the majority. And we also get a lower overall bias towards option A. And if we look at how that plays out collectively, the most striking feature is that we get much more consensus, but also a much larger percentage of these sort of catastrophic errors where everyone is choosing the wrong side. So we're up to about 18% of those at this point. And if we take our discount factor even higher, so if we anticipate far more about what rewards we get in the future, then this situation only gets stronger. So now all of our contour lines pretty much lie exactly along the center. Agents almost always follow the majority, and we have nearly 30% of occasions where the whole group just chooses the wrong choice. So we're seeing that there's clear price to pay for this extra sociality. So if you're more social, you'll get more collective wisdom in the future. But at the same time, that collective wisdom is overall going down because agents are bringing less independent information to the party, as it were, and relying much more on what each other have done. So we can map that out and look at how accurate groups of different sizes are in terms of their sort of future consideration. So if we look, if we model the discount factor in terms of the expected number of games that the agents are going to play in the future, we can see that groups from 1 to 10, there's a clear pattern where larger groups can do much better than individuals when there are very few games to consider in the future. So we get expected accuracy here of about 0.78, so 78% of agents are getting the decision right, compared to 66% of agents by themselves. So I've set the noise parameters to make it so agents can be 2/3 accurate by themselves. But if we increase the discount factor, which means that we care more about the future, this accuracy rapidly comes down, but maintaining the property that larger groups are still better than smaller groups. So the trade-off is always that the agents will make their collective accuracy lower by being more social, but they'll maintain access to the larger group, which is better than being in the smaller group. And so where they place themselves on that trade-off depends on the value of gamma. So what else can we do with this model? Well, so far we've considered a completely homogeneous group in which everyone has the same discount factor. But what we might ask is, what sort of behaviors do we see as we introduce heterogeneous agents into a group? So on the left-hand side, what you see, firstly, are a red and black line. These represent, in the red line, what the social response that a group has if you have a very strong caring for the future. So if gamma is 0.99, on the x-axis, you see the difference in the number of agents who've already chosen A and B. So this is the size of the majority for A. And you see essentially a step function. So agents almost always follow the majority. If agents didn't care about the future, which is the black line, then you see a rising curve, but there's a considerable probability to choose B, even if the majority has already chosen A. Now, if we imagine introducing one agent who doesn't care about the future into a population who otherwise all do, then that new invading agent will actually follow the curve shown in blue here. So this again looks like a step function, but it's much more elevated on the left-hand side. And what happens here is that the agent who doesn't care about the future recognizes that all the others are merely following each other. And so it essentially treats them as if they were just one agent by themselves. It doesn't care whether it ends up in a group with them after this decision. So if they choose A, and here A is assumed to be the correct choice, so that's where the strong signals are coming from, it will generally follow them, and you get much the same behavior as you would otherwise have. But if they've all chosen B, even if you've got a very strong majority in favor of B, that agent who doesn't care about the future still has a very high, roughly 50-50 probability to choose A instead, to go against the majority and follow the private signals that it's getting instead. So it essentially can...
Two more minutes, okay?
2 more minutes, okay, yeah. And then the last thing I wanted to say then is the last game we can sort of play with this is we can ask, what should we think if we see groups behaving in different ways? So if we have a group that doesn't care about the future, we generally expect that the more agents who choose A, the more strongly we as the external observer should believe that A is the correct choice. What happens for groups that have this conformity bias, because they're trying to stay together for future decisions, is that this monotonicity is broken. So if you have a group that expects to play 100 or even 1,000 games in the future, we know that situations where they end up all making the same decision are likely to be the situations where they all just followed each other blindly. And so actually we should trust their majority outcome far more when it's a majority but not a consensus. So we see on the curves here that what we should place as the probability that A is right is actually highest when there's a considerable amount of disagreement between the agents. So just to summarize a couple of points, we've seen that the caring about the future gives you a great incentive rationally to stay in a larger group because you can access collective wisdom later. And the more you care about the future, the more social you should be. And also the more that you think your future group status is contingent on the decisions you make now, the more rationally social you should be. That increased sociality comes at a cost in terms of immediate accuracy. So because we're not paying as much attention to our individual information, we make less accurate decisions immediately as the price to pay to stay in the group. Those who don't prioritize staying in the group can often act as leaders because they will make decisions that others can't because they can buck the majority. And when we see groups that probably do have this conformity bias, disagreement is likely to be a good signal to us of collectively wise groups, both because it indicates something about the value of the private information individuals had, but also if we don't know what the conformity bias is, then groups that disagree more are probably those that have weaker conformity bias, and as we've seen, that means they're likely to be more accurate on each decision. And you have a screenshot here of the paper where you can see more of the mathematical details. I'll be happy to take any questions.
All right, thank you so much, Richard.